All right, so here is a document that I had written. It's posted for us in D2L. This is unpacking Green's theorem. So I'm not just going to sit here and read the document to you. I encourage you to read this on your own time, but I wanted to make a video to call your attention to it. This document here, it does walk us through sort of what Green's theorem is and why might it be true. It's not a proof of Green's theorem. That's a bit more involved. But this is sort of your building intuition for it, why it should be true. And it also answers some questions that I think questions that are natural to have. So for myself, in my own experience, first learning Green's theorem, I had a lot of questions. I mean, I had three big questions, maybe not 40 questions, but I had some bigger questions. So when I read Green's theorem, so at the very top here, the theorem statement starts right here and ends right here. So suppose del D is a simple closed curve oriented counterclockwise, and it's enclosing a region D of the plane, two-dimensional Euclidean space. If we have a vector field, capital F, whose components are F1, F2 on R2, then the line integral over the boundary of D, f dot dr, so a line integral, a vector line integral, that is equal to the double integral of this quantity, the partial of f2 with respect to x minus the partial of f1 with respect to y. So here are my three questions. So when I first saw that, and even later, after I got my degree, my bachelor's in math, and I went on, to grad school, there was wondering some questions about this. And to me, when I see this, I think of, first of all, why is counterclockwise orientation important? Why is that needed? Does it not work at all if it's clockwise? What happens if it's clockwise? Is clockwise bad? Is counterclockwise better? So there seemed to be this weird, what I would now call an asymmetry. Why? Because really, in math, it shouldn't actually matter what you call things or how you measure things. Sure, it matters in the answer, but only something arbitrary that's very easy to deal with, like a negative sign, you know. So it just seemed a little bit strange. I also wondered, what is the significance of the integrand in the double integral here? So this quantity right here, this looks weird. Maybe not that weird to some of you, because you might recognize this as the thing. If this were an equal sign, right? These two things being equal is what is the condition for a vector field in two dimensions to be conservative, provided it's defined in a simply connected domain. So this showing up here, sure, with a minus sign, but remember here that if you have del f2 del x minus del f1 del y, you could just add this to the other side. Excuse me. If you think of this as being equal to 0, then adding this to the other side, you just get them being equal. So there seems to be some sort of connection here, possibly with conservative vector fields. But I do want to be very, 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 very clear here. Not the point of this video, but also I don't want to lead anybody astray. There's nothing in here that mentions conservative vector fields. So Green's theorem has nothing to do with conservative vector fields, but this quantity is important. It's important enough that it's used and it characterizes when a field is conservative or not. So it does show up here, but you do not have to have a conservative vector field to use Green's theorem, just to be 100% clear. And then the third question I had was, how can a line integral be related to a double integral? I just don't see how right? This is like a one-dimensional kind of thing. This is a two-dimensional thing, and the geometrically what this represents is a volume, and geometrically what this represents, it's sort of like it's a little bit harder. I mean, it's technically still like the area of some curtain, kind of underneath of an appropriately defined and related surface to this F. It just seems very strange to how these things have seemingly different dimensions. They're sort of related to different dimensions, so how can they be equal? So there seem to be some weird questions here. So, like I said, I'm not going to go through this whole thing. I would like you to read it all. I think it's a great read. Um, but in particular here, I do want to just say, so that you get the quick answers. If you want to really dig in, then we can take a look at it here. Um, why is counterclockwise needed? The short answer, it's not. It's not actually needed. Kind of. There's nothing inherently better about clockwise versus counterclockwise. There's not. Really, what happens up here is if we choose to orient this clockwise, then the order here switches. That's it. That's the only difference. So essentially, if we don't tell you what the orientation is, students or people who are just learning this for the first time, if they don't know that the orientation here affects the order over here, then naively you would probably still compute this because this is very well defined. This, then that. Where here, you are free to parameterize a curve in any way you'd like to. So there's a chance that this left-hand side, when you go to parameterize this, you could be parameterizing it in a way that's not counterclockwise. In which case, this right-hand side, you would compute it as is because this is pretty concretely stated, I think. But really, it would be wrong in that case if you were to do this clockwise. So really, this is just to make sure that telling you if you do it counterclockwise, this is the setup here. So in that sense, it doesn't really matter. All right. The second thing, and this is really what I wanted to create the video for, is just to elaborate on this a little bit more. I think it helps to see a visual or a video with it. So what's the significance of this integrand? Why is that needed? Well, because we are orienting things counterclockwise, let's just say we want to know what is the tendency of a vector field to curl or to rotate in this counterclockwise direction. So if we've got a vector field, so here I'm visualizing vector field lines, and then the length of these lines, the magnitude, is to communicate to you, we're imagining this vector field F. Let's imagine it to be a force acting on this block that is in the vector field and is affected by it. Well, if we have longer vectors over here, then that means there's a larger force on this side of the block than there is on this side of the block. So then this block would tend to rotate a little bit counterclockwise. Just imagine you have something on a table and you push it on the right-hand side. As viewed from above the table, that object would rotate counterclockwise. Similarly, if our object's oriented in the y direction lengthwise, so this was oriented lengthwise in the x direction, now we're in the y direction. In this case, the vector arrows, they get longer as we move upward. And then if we have a greater force on the top, this would also cause it to rotate counterclockwise. So what's changing here? Well, if we think of our if we think of our vector field as F1, F2, then what's happening in this first picture? Well, in this first picture, as we move to the right, so as we move in the x direction, what is happening to F2, which is the y component? Well, it's getting bigger. So F2 would be increasing as x increases. So that's exactly where we get this from. Over here, this one's slightly, just a little subtlety here. It is true that as y increases, the length of the vector increases. But what we're talking about here is not the length of the vector that we're interested in. We're interested in which component is changing and how is that component changing. So what's changing as we move upward? The x component's changing. The x component is technically decreasing. Technically it's decreasing. Why is that? So down here you can think of this vector as maybe like -1, 0. This vector maybe -2, 0. And this vector up here maybe -4, 0. Sure, it's getting bigger in the negative direction, but that's decreasing. So that's why this is a less than 0. So just be careful there. We're not talking about, it seems like we're talking about the length, because the length is important, but for these partial derivatives, we're examining the components themselves, which is distinct, although related to the length, is a distinct notion from the length. So that's how we're getting these two quantities here. And it's also important to know that this is telling us counterclockwise. This sort of characterizes counterclockwise rotation as viewed in the x direction, where this one here does counterclockwise rotation in the y direction. But because this one's negative, really what we're saying here is actually this characterizes counterclockwise rotation when moving in the y direction. Without the negative, just making this positive, then that actually characterizes clockwise rotation. So that's why down here, our integrand, we're really summing these two things up. We want to know the rate, the amount of the rate that's contributed by counterclockwise rotation in the x direction, plus the amount that's the amount of the rate that's contributed by rotating in the y direction. So because this is negative, that's why we're adding a negative quantity. We're like adding this, really. So this is really just the sum of two different rates. They're both rates of change that are describing counterclockwise rotations. This one is the amount contributed by x movement, and this one is contributed by amount of y movement. So together, this is the net rate of counterclockwise rotation. So that is what we are essentially adding up. So if we now look further, down here, how is a line integral related to a double integral? Okay, so let's imagine we've got some domain that satisfies the hypotheses of Green's theorem. So we've got we have a bounded region, and that region is bounded by a simple closed curve, and it's oriented counterclockwise. You can see that by the orientation markings drawn on the curve. So imagine now that we take this and we overlay a grid. So we create a grid, and let's make this grid very, 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 very fine. So imagine like nanometers or something like that. We very finely partition this grid up. So if we do that, we should get something like this. And of course, I'm not going to make the grid size actually nanometers, because then what can we talk about? But we can, at the very least, imagine what's going on here, even if it's coarser and more zoomed out. So essentially, let's look at a small patch. We can look at the whole thing, and what we're going to talk about in this small patch here will generalize to the whole thing, but let's start with looking close in here. So in here, it's hard to see, but there's a 3 by 3, so there's 9 individual squares, And then we'll go ahead and zoom that in and look right over here. So now if you look here, essentially this quantity, del F2, del x, minus del F1, del y, tells us the counterclockwise rotation. So I'll say the rate of counterclockwise rotation. So effectively, what we can think about is that at every single point, every single point in the domain D, we sort of have a way of describing what's the counterclockwise rotation rate. Again, this is not a proof by any means. This is sort of just building intuition. So what we can do is we can actually think about each of these grid lines as rotating. Okay? So now what's going to happen here is that if we break this up and do the line integral over this piece, right here, if we do this line integral, that what's going to happen to these edges here, these interior edges that are shared by other squares, on the one side, it's the same edge in space, so the amount of rotation is going to be the same. The amount of rotation is going to be the same. But in this orange square, we're going upward. But for this square here, when we go counterclockwise, relative to this first square, we get this, right? So the one's going upward, the one's going downward, so things will actually cancel out because the orientations are, oops, meant this way. The orientations are opposite. So the line integral, if we look at it at this edge, so the line integral of f over just this edge would cancel out because we'd have a line integral from this edge from the orange square, and then later on we'd have a line integral from this same edge but going in this direction because relative to this square that's counterclockwise. So at all of these interior edges, the line integrals would cancel out. So what's left over here is just an integral around the boundary. Which is exactly why, now there's a lot more details in this proof if we're going to generalize it and actually prove it, but it's this reason, it's that very reason why if you actually create a sufficiently finely partitioned grid, then you basically get all the interior edges cancel out and you're just left over with the line integral around the boundary of the object. That is the intuition, that's the justification. It's that they cancel out all the interior line integrals. All right, hopefully that helped you build some intuition as to what is going on in Green's theorem and why it is the way that it is.